To this particular problem, we are going to perform thermal analysis on a composite slab. Here there is a composite slab with 4 different materials, and here we are going to give the temperature, and here also we are going to give the temperature, and then we are going to give the thermal conductivities of this particular 4 materials, and then we try to find out the temperature distribution inside this composite slab, and also we are going to find out the heat flux that is generated at this particular surface of the composite slab using Ansys Workbench. Thank you. The problem of composite slab, I have opened Ansys Workbench. In the Ansys Workbench, I am going to take the steady state thermal and drag it and drop it on the project schematic. Once I place it on the project schematic, I am going to double click on the engineering data, and I am going to add 4 materials named A, and then B, then C, then C and D. I have created 4 materials. For those 4 materials, I am going to take this isotropic thermal conductivity and give that particular property to this 4 materials. So once I give this particular property to 4 materials, I need to enter the value. The value of the thermal conductivity we were given in watts per meter Kelvin, and here it is watts per meter centigrade. We need to change it to watts per meter Kelvin, then enter the value. For this D material, it is 0.04. Then coming to C material, I need to change the unit again, and the value is 1.7. And then coming to B material, the value is 0.12. Coming to A material, the value is somewhere around 0.038. So once I have given the required thermal conductivities, I am going to close this engineering data. And right now I am going to just right click on the geometry, say import geometry and browse, and I am going to select this composite slab, and I am going to press OK. So now I am going to double click on the model cell in order to open Ansys Mechanical to apply the required temperature loads and solve this particular problem. So once the Ansys Mechanical opens, what I am going to do is I am going to expand this geometry group, and I am going to select this object, and I am going to give the material A. Then I am going to select this slab, and I am going to give the material C. And then I am going to select this slab, I am going to give the material of D. And I am going to select this slab, I am going to material A. Sorry, it is B. As per the problem specification, we have given this particular block is made up of material A, this is B, this is C, and this is D. In that particular order, I have assigned the materials. Once I have completed assigning materials, my next option is I need to right click and say insert and go to temperature. As I have already told you that temperature, convection, radiation, heat flow, perfectly insulated, heat flux, and internal heat generation are the type of boundary conditions that are available with steady state thermal analysis. In this particular problem, we are going to take the temperature, and we are going to apply the temperature to this particular phase. I am going to apply, and the temperature at this particular phase is 80 degrees. So I have given 80 degrees. Then coming to this particular phase, the temperature is 25 degrees. So I am going to right click, insert, say temperature, and I am going to insert 25 degrees of temperature. And once I have given the required temperatures, then what can I do is I will right click and say solve, because what happens, these two temperatures are only the boundary conditions for this specific problem. So once I have solved the particular problem, right now what I am going to do is I am going to select insert and go to thermal. I am going to click the temperature, and I am going to right click and say evaluate results. Now you see this is the distribution of the temperature inside this particular composite slab. You can even animate this particular results. See here, you can just play and animate how the temperature is being distributed inside this particular composite slab. Right now the next option or the next result we need is what is the heat flux that is generated at this particular area. So what I am going to do is I am going to right click, say insert, go to thermal, go to total heat flux, and in the total heat flux also I am going to select only this particular phase. So for that purpose I am going to go to the geometry and then select this particular phase and say apply, and once I apply the total heat flux result, I am going to right click, say evaluate all results. Once I say evaluate all results, I am going to get the heat flux that is generated at this particular phase. So this is the heat flux that is generated at this particular phase. So this is how we can solve a problem of a composite slab and find out the temperature distribution inside a body, or otherwise we can also find out the heat flux generated at a particular area using Ansys Workbench by performing steady state thermal analysis. Here in this particular problem, the mode of heat transfer was conduction, because what happens, there was a physical contact between the blocks of different materials and heat was transferring through the physical contact or molecular contact, which can be known as a conduction. In the next lecture, I am going to teach you how we can use convection boundary conditions and simulate the heat transfer through convection conditions using Ansys Workbench. Thank you. In this particular problem, we are going to perform thermal analysis of a fin tube structure. This particular fin tube is prepared out of aluminum alloy, and here, due to the symmetric nature present inside the geometry, we have only modeled quarter geometry only. Then this particular tube carries hot fluid in the interior region, and there is a convection condition at the exterior region. So what we need to do is we need to apply a uniformly varying temperature load on the inner surface, and then we need to find out the temperature distribution throughout this fins using the convection mode of heat transfer inside Ansys Workbench. For analysis on this aluminum fin tube, I have opened Ansys Workbench and I am going to take this steady state thermal, place it on the project schematic. And now I am going to double click on the engineering data, go to engineering data sources, then go to general materials library. In the general materials library, I am going to select this particular aluminum alloy and add it to my present analysis. And once I have done this, I am going to close the engineering data. Then I am going to right click on the geometry cell, go to import geometry, go to browse, and I am going to select this particular fin tube and I am going to open it. And once I have imported the geometry, I am going to double click on the model cell in order to open this Ansys Mechanical to perform the further analysis. Here there is a special requirement that we should be applying not a uniform temperature, but we should be applying a uniformly varying temperature on the interior face of this particular fin tube. So this can be done through equations. So we are going to see how we can apply that equation. So once this particular geometry has opened, I am going to go to the geometry and I am going to just change it from the structure steel to the aluminum alloy. So once I change the material assignment, now I am going to just right click, say mesh. So once I generate the mesh, then we are going to apply the boundary conditions. The first boundary condition is the temperature, and that too uniformly varying temperature. As specified in the problem, what happens at this starting, the temperature is around 200 degrees. At this particular exit, the temperature is around 150 degrees, and it is uniformly varying along this particular length. So what happens, we need to be simulating that particular condition. So in order to apply the temperature, right now what I am going to do is I am going to right click, say insert, go to the temperature boundary condition, and I am going to select this particular interior face. And once I select this particular interior face, I am going to apply it in the geometry selection. And now here if I enter the value, it will be a constant value across this particular face. But what do I want is the uniformly varying temperature which starts at 200 here and which ends at 150 degrees at this particular end. For that purpose, what I am going to do is I am going to change this from constant to function. And once I change it to function, then I need to give the function value. The function value is 200 minus 0.25 into y, and this particular y ranges anywhere from 0 to 200. Okay, so what happens if this y is 0, then 200 minus 0.25 into 0, the temperature will become 200. Likewise, if the y is 200, 200 minus 0.25 into 200, which means 200 minus 50, it will become 150 degrees. So this is how you can apply uniformly varying temperature. If in the case of a structural analysis, you can use the same equations to apply uniformly varying loads on different structures. And once the temperature is applied, then we need to give the convective boundary condition. Here we need to give the convection, which is a temperature dependent property for this particular problem. For that, what I am going to do is I am going to right click, say insert, go to convection boundary condition, and first of all let me select all the outer faces so that I can apply the convection boundary condition. So once I have selected all these particular exterior faces, now what I am going to do is I am going to select apply, and once I select apply, now I am going to, instead of giving the film coefficient as a constant, I am going to change it to tabular. And once I change it to tabular, here in the tabular data it is asking us what is the independent variable. Here for this particular problem, the independent variable is the temperature. So I am going to select temperature. So once I select the temperature, here see a table has been updated. Here we need to give the temperature, and based upon the temperature we have given in this particular column, we need to give the convective coefficient. So at 0 degrees the convective coefficient is 0.04. Then at 10 degrees it is 0.054, and at 20 degrees this particular convective coefficient is 0.06. Likewise at 40 degrees it is 0.066, sorry, it is 0.066, and then at 60 degrees it is 0.0007, and at finally 100 degrees centigrade it is 0.0077. So this is how our convective film coefficient is going to vary with the temperature. So here you can see the variation of this convective film coefficient with respect to temperature. So once we have given all this convection condition and temperature, we are going to right click and say solve. So before going to solve, I need to define this say ambient temperature as well. The ambient temperature is around 20 degrees. So I am going to give 20 degrees ambient temperature, and I am going to right click, say solve. Once I solve this particular problem, I am going to just right click, say insert, go to thermal, and I am going to select the temperature, and I am going to say evaluate all results, and I am able to see the temperature distribution inside this aluminum fin tube. Likewise, see for example, if I am going to right click and say insert and go to this thermal and go to directional heat flux, I can select this particular surface, or otherwise I will leave it to all bodies, and I am going to just right click, say evaluate all results. I can see the heat flux through every surface of this particular aluminum fin tube. So this is how you can solve aluminum fin tube problems or convection heat transfer mode problems using Ansys Mechanical or Ansys Workbench. In the next lecture, we are going to see how to model the radiation mode of heat transfer using Ansys Workbench. Problem, we are going to model the radiation mode of heat transfer using Ansys Workbench. So here we take a heating coil and we try to pass electricity through this coil. Due to the resistance present in this coil, heat is being generated, and due to the vacuum present inside this particular glass tube or glass bulb, this mode of heat transfer will be through radiation. So we are going to simulate internal heat generation, and also we are going to put up radiation boundary conditions, and we are going to test out this heat transfer using Ansys Workbench. Problem of heating coil. I have opened Ansys Workbench, and I am going to take this steady state thermal and place it on Project Schematic. And now I am going to go to engineering data, go to engineering data sources, go to thermal materials library here, and in the thermal materials library I am going to select this tungsten. Once I select it and add it to my project, I am going to close the engineering data. Now I am going to right click on the geometry, and I am going to say import, and I am going to browse, and I am going to select this particular heating coil, and I am going to press open. Once I have imported the particular geometry, I am going to double click on the model cell in order to open Ansys Mechanical and perform the further analysis. Here the mode of heat transfer is through radiation, so we need to give emissivity as well as this ambient temperature as an input. So once I have opened Ansys Mechanical, the first and foremost thing I need to do is I need to go to this heating coil geometry and change the material from structural steel to tungsten. And once I've changed this particular material, right now what I'm going to do is I'm going to right click on the steady state thermal, say insert, go to this particular internal heat generation option, and I'm going to select the total body because internal heat generation is a property of the total body. I have selected the total body and I'm going to press apply. Once I have selected the geometry, I need to give the magnitude of this internal heat generation, which is around 0.02 watts per mm cube. And once I have defined the internal heat generation, now I need to define the radiation boundary condition. As I've told you, radiation boundary condition is a surface property. So I'm going to just right click, say insert, and go to the radiation, and in the radiation I need to select all the external surfaces. For that purpose, what I am going to do is I am going to select this particular surface first, and I am going to go to this, and I am going to set extend to limit, so that what happens, this particular surfaces along this total path will be selected. And once I have selected all the surfaces through this particular option, I am going to press apply. Once I have applied this particular radiation to the surfaces, I need to give the emissivity. Our emissivity value is 0.25, and I need to give the ambient temperature, which is around 30 degrees centigrade. Once I have given all the required conditions of internal heat generation and radiation, I am now going to right click on the solution and I am going to solve. And once the solution is solved, we are going to find out the temperature distribution and the heat flux inside this particular coil. Then once the problem is solved, I am going to right click, say insert, go to temperature, and I am also going to right click, say insert, go to thermal total heat flux, and I am going to right click and evaluate both of these results. And once I evaluate both of these results, right now I am going to select the temperature, and I can view the temperature distribution inside the coil. And I am going to select the total heat flux, and I can visualize the total heat flux present in the coil. Then coming to this, we can also see all these results in the form of vector arrows. So what happens if I put up vector display instead of contours being displayed, all the values are being displayed with this particular lines or arrows. So what happens, these arrows are going to show the magnitude as well as the direction. So the heat flux, the heat is coming out of this particular coil, so it is showing the direction that the heat is coming out of this top surface of this particular coil. You can also change the size of these arrows by just using this slider, and you can also change the display of the arrows by using these options and this particular option. Okay, so this is how you can use vector displays, and this is how we can simulate the radiation conditions using Ansys Workbench software. Then coming to the energy balance, as I have told you in assumptions, there should be energy balance when we are performing this steady state thermal analysis. So what is the amount of heat generation that we have applied to the coil? It is nothing but 0.02 watts per mm cube. Then what is the volume of the total coil? You can just go here to the geometry, and in the geometry you can go for the properties, and you can see the volume. It is nothing but 15,978 mm cube. So what happens, 15,978 into 0.02 will yield you around 324 or say 320.5 watts of energy. So for that purpose, what I am going to do is I am going to right click, say insert, go to the probe tool, and you can put up the reaction probe. And once you put up the reaction probe, you need to select the boundary condition. So here the radiation is the boundary condition that I have selected, and I am going to just evaluate this particular result. And once I evaluate the result, see here the value is equivalent to minus 324.88 watts, which is somewhat very near to our analytical calculation. So what is happening, as we are performing a steady state thermal analysis, the energy balance is there. So this is how we can also confirm that our analysis is somewhat good. Then in the next lecture I am going to show you how to perform thermal analysis on a solenoid, where the mode of heat transfer will be a combined mode, where we have a convection as well as conduction mode of heat transfer in that particular problem. We are going to perform thermal analysis of a solenoid. What happens, this particular say solenoid has a cast iron core with polyethylene insulator, and then it is a copper coil surrounding it, and then there is a fixed base plate which is made out of structural steel. So what happens, we are going to have a fixed temperature here, we are going to have a convection condition on these surfaces, and we are going to have an internal heat generation in the core, and we are going to find out what is the heat transfer or what is the temperature distribution inside this particular solenoid, and also we are going to plot the variation of temperature along the width of this particular solenoid using Ansys Workbench. Analysis on this particular solenoid, what I am going to do is I am going to take this steady state thermal and place it on the project schematic, and I am going to engineering data, I am going to engineering data sources, and now I am going to general materials library. In the general materials library I am going to search for grey cast iron and then polyethylene, and then structural steel is by default applied, so I need not add it once again, and I also need to go for this copper alloy. So once I have selected all the required materials, then I am going to just close this engineering data, and now I am going to just right click on the geometry, say import geometry, and I am going to select browse, and in the browse I am going to select this particular solenoid, and I am going to press open. And once I have imported the required geometry, I am going to double click on the model cell in order to open Ansys Mechanical. So once this particular model is open inside Ansys Mechanical, the first thing is I am going to set up the materials. For the bracket, the material is structural steel. For the core, the material is cast iron. So for the insulator, the material is polyethylene, and for this coil, the material is the copper alloy. So once I select all the required materials, the next thing I need to do is I need to right click and say generate mesh. And once I generate the mesh, then we are going to apply the boundary conditions. In order to apply the boundary conditions, I am going to right click, say insert, and take this particular internal heat generation option, and I am going to select this core, and I am going to press apply. The magnitude of internal heat generation is 0.01, and I have entered this particular value, and I am right now right click and say insert, go to the temperature, and then I am going to select this particular phase. So in order to select the phase, I need to go to this selection toolbar, select the phase select tool, and then come back and select this phase and say apply, and the temperature is 25 degrees. Then coming to the next boundary condition, I need to insert a convection condition. So I need to select all the top faces. So what happens, the convection is going to take place through this top surfaces, and once I select all these surfaces, I can press apply, and the film coefficient of this particular problem is 5E minus 5 watts per mm square degrees centigrade, and then the ambient temperature value is 25 degrees centigrade. And once I have entered all the required values, now what I am going to do is for this plate I am going to give a perfectly insulated condition on the other three sides. So that means no heat can enter or no heat can go out through this particular boundary condition. So I am going to select this perfectly insulated boundary condition, and I am going to select this face as well as this face. So once I have selected the three faces, I am going to say apply, and once I have applied all the boundary conditions, I can just right click and say solve. Once I solve this particular problem, I am going to right click, say insert, go to thermal, go to temperature, and I am going to right click and say evaluate all results, and see the maximum temperature is at the core. This particular insulator at the middle is keeping this particular heat from going away to this copper alloy or the copper coil. Then coming to the next stage, we need to create a path, and we need to define a path through which we need to graph the change of or variation of the temperature. For that purpose, what I am going to do is I need to create a path. So as I have shown you earlier that we can select any edge to create a path. Here what I am going to do is I am going to create two coordinate systems, and I am going to place a path between origins of those two coordinate systems. For that purpose, I need to go to the coordinate system, say insert coordinate system, and in the coordinate system, instead of defined by geometry selection, I am going to change it to global coordinates, and once I change it to global coordinates, I need to give the values of its origin. So the origin is at 23, 50 and 4 mm. So this is nothing but a point on this particular face. Then I am going to right click, say insert. I am going to create another coordinate system. I am going to define it by global coordinates, and I am going to give the coordinates here. The coordinates are 23, 50 and 38, and once I have created these two coordinate systems, I am going to go to the model branch. I am going to select the construction geometry, and in the construction geometry I am going to select to create a path. And once I select the path, here in the path type you can just give the starting coordinate system as well as ending coordinate system. So the starting coordinate system is, I am going to change it from global coordinate system to the coordinate system 1, which I have created now, and then the ending coordinate system also I am going to change it to coordinate system 2. And now see, a path has been generated between these two sides of the solenoid. Now what I am going to do is I am going to plot the temperature along this particular path. I need to go to the solution, say insert, go to thermal, go to temperature, and instead of this geometry selection, I am going to change it to path, and I have created only one path, so in the path I am going to select that path. And once I have selected that path, I am going to right click, say evaluate all results, and I once evaluate the results, see here a graph has been shown. So what happens, as the length is going this side, the temperature variation is shown here on this particular y-axis. So this is how you can create different paths, and you can plot different values. Even you can apply this technique in the structural analysis as well to plot stresses and strains and other sorts of output which you want or which you require. So this is how you can perform an analysis, a coupled thermal analysis, where two or more different modes of heat transfer may be there using Ansys Workbench. In the next section, we are going to deal on how to perform thermostructural analysis on different industrial problems.